Hi everybody. So we've been learning about linear interpolation and lerping. So now I want to shift a little bit towards nonlinear interpolation. So let me first explain the problem here. So pure lerp, that's an R, pure lerp, it has a rigid, like a very unnatural and rigid starting and stopping. Okay, if we look at the example, it just suddenly starts to full speed and suddenly stops. Same thing goes for change of direction. Okay? Another way to say that is there's no acceleration and there's no deceleration. No deceleration, okay? This looks very rigid and it looks really unnatural. Looks like an old-fashioned video game. It doesn't look like how the real world works. So let me open up an example. So what I've done here is I've taken our previous example of keyframes and I just changed it up a little bit. But what's important is I made the keyframes a little more erratic and I added a button such that if I push a key, it'll stop at the end of the next keyframe. So watch this. So here's our example. And you can see it's moving around. It changes direction erratically. It moves rigidly. And when it stops, if I click stop, it just stops suddenly. When it starts, it just starts suddenly. The real world doesn't work like this. In the real world, things slow down, things speed up. So this looks okay. It's kind of exciting to if you do it for the first time, but very quickly you realize, yeah, that's not how things work. Okay? So standard lerping has this rigid start and stop problem. The reason why this happens, if we think about it, is because as we map our t, it gets a linear mapping to our output. So let me just maybe draw a diagram to help out here. So this is my t value here. So this t value goes from 0 to 1, and this is time. Okay? Over time, you end up getting just a straight line, hence the name linear interpolation. Okay? And as I go along a unit of time, t changes exactly the same. It starts at full speed, it stops at the same speed as it started at. The rate of change is exactly the same the whole time. So this is because t of 0 to 1 maps linearly to the output. Oops, OUTP. Okay, it maps linearly to the output. Another way to say it is over time, the change in t, how much it changed, the rate of change, its speed, it's not change in, its change in t is constant, okay? So you don't have any starting or stopping. So what we want is something a little different. We want to simulate acceleration and deceleration. Okay, what we need to do, we need to be nonlinear now. We want to have, at the beginning t should move slowly. And then it goes full speed. And at the end it should maybe move slowly again. So as we go from t0 to 1, we don't want it to be linear anymore. A non-linear treatment of t. Okay, so I'm going to draw this, what this might look like. Here's an example. You can imagine if as t went from 0 to 1 over time, as t changes over time, you could imagine in the first unit of time, t changed very little. And as time goes along, t gets faster and t changes faster. This is a acceleration. And you could imagine the opposite too. You could imagine this pattern where t starts out changing very rapidly over time. Within very quick time, it changes very quickly. But then as time goes along, it slows down and the rate becomes asymptotic almost. It slows right down. So as time goes along, let me just mark these points here. And I'll mark this is a 25%, 50%, 75, and 100. At 25%, the bottom curve, the accelerating, is still, the t is not very far along. It hasn't moved very much yet. Linear somewhere in the middle. And the other one, it's already quite fast. It starts out quite fast. By the time we hit 75%, the accelerating, the speed is getting up there, right? But the top one, the decelerating one, it started to slow down. The actual difference between this one and this one, you can see the height there. This difference is small. It's slowing down. And finally, at the end, it's barely moving at all. Whereas the other one, in the same span, look how much the speed changed. It's going really, really quickly. So maybe pause the video and spend some time with this graph. It'll help out with the rest of this unit. Okay? The idea being the green line is linear, and we have these two pink non-linear lines that show acceleration, where t starts out slowly and gets fast, and deceleration. T starts out fast and gets slow as we move towards the edge of it. So instead of linearly, regular linear change in t, over time, we need a way to change it non-linearly. Instead of a regular linear change in t over time, we need a new way to modify t. Okay, and if we look, excuse me, if we look at our old one, t, excuse me, I'm going to pause the video and get some water. All right, I survived that. T is going to be, our old formula for t is I over n, where I is the current frame and n is the total frames. You can see that as I gets bigger, t jumps up by the same rate every time, which is what gives us this linear result. Okay? Cool. So this is the problem we have. We want to find some way to make this not a straight line anymore and have these acceleration or deceleration curves. I'm going to stop here and come back and just quickly go over one approach to getting nonlinear interpolation. Okay?